Welcome to our Intermediate Experiments series. My name is Aaron Dolan, and today we're going to explore the input impedance of op-amps, specifically the differences between the inverting and non-inverting stages. To do that, we'll briefly explore the configurations and the gain equations for both inverting and non-inverting. We'll briefly touch on the concept of Thevenin's theorem and how that's applicable to the various sensors that you will be connecting your op-amp to. We're then going to use the math to describe or to calculate what the output is going to be, and then we'll see if we are indeed correct by hooking up the function generator and the oscilloscope to view the results. This is the circuit we'll be using today. It consists of an LM358 op-amp with the lower section, which is to say the A section, set for non-inverting with a gain of 10, and the upper section set for inverting, again with a gain of 10. Part A of the LM358 is used as non-inverting, Part B as inverting. Let's not forget the power supply connections on pin 8 for 5 volts and pin 4 for -5. You recall the gain equation. So gain is equal to negative RF over Rin, where our RF is 100K and our Rin is 10K, which gives us negative 100K over 10K, or simply negative 10. For the non-inverting stage, gain is equal to 1 plus, in this case, we'll say R2 over R1, which yields 1 plus 180 over 20, which is giving us a gain of 10. So both stages are set for the same gain. Again, a gain of 10 for the non-inverting and a gain of -10 for the inverting. With that said, we can get to the heart of our video, and that is the topic of input impedance. Now, you'll notice that we've used a 100K ohm resistor in a series with the signal source. You could think of that as V Thevenin here and R Thevenin. From your studies of electronics, you may recall that Thevenin's theorem tells us that any two-terminal device may be modeled as an ideal voltage source with a series output resistor. In this case, we're using the signal generator, but it's a good stand-in for a sensitive sensor. What we're concerned about here is that if you were to stand here and look into this op-amp, what would the impedance be? Likewise, if you were to stand here and look into this op-amp, what would the impedance be? And it matters because what will happen is if the input impedance of either op-amp is low, the voltage at this point right here will drop. Let's consider the non-inverting stage first. So we're going to connect our Thevenin source directly to pin 3. In the ideal world, the input impedance would be infinite, which is to say the voltage here and here would be the same, right? There would be no voltage drop across that 100K ohm resistor. As an example, if we let the Thevenin voltage be 100 millivolts, we would expect there to be 100 millivolts at the input of the op-amp, and because it has a gain of 10, we would expect to see 1 volt on the output. Again, that's the ideal case. The LM358 is not ideal, but as we'll see in the lab, it comes pretty close, and this is almost exactly what we're going to see. Things aren't quite the same when we talk about the inverting amplifier. So if we connect up our source with its 100k ohm Thevenin impedance. And then we look into this op amp. What do we see? The answer lies at this point right here, which is known as a virtual ground. In simplistic terms, we know that the op amp has high gain and that it will tend to drive the difference between the input signals to 0. Since pin 5 is connected to ground, we can expect that pin 6 will essentially be at ground. Consequently, if you're over here looking into the circuit, what do you see? Well, all you see is this 10k ohm resistor, which is connected to ground. Given that our Thevenin resistance is 100, we've essentially formed a voltage divider, with the voltage at this point here being the input to the amplifier. Using a voltage divider, V in is equal to 10k over 10 plus 100 multiplied by V Thevenin, which means our input to the op amp will be 0.09 V Thevenin. If we were to let V Thevenin equal 2 volts, it follows that V in would be 0.18 volts. Given that the op amp has a gain of 10, we would expect V out to be about 1.8 volts, which is a really interesting result because we've taken our Thevenin voltage of 2 volts, essentially ran it through a voltage divider, giving us a V in of 0.18, and then we've multiplied it by a gain of 10, giving us 1.8 volts. So our output voltage is actually less than our Thevenin voltage because of the input impedance loading down our Thevenin. That's quite the trap if you weren't expecting it. And it could be worse. For example, let's change this to 1K and this to 10K. You'll notice that this hasn't changed the gain of the amplifier. However, it has certainly changed the input impedance. So now instead of seeing 10K, you see 1K. Watch what happens when we use the same Thevenin voltage. So we'll let V Thevenin equal 2 volts, which gives an output voltage of, let's see, remember we need to do a voltage divider here, of 1 over 1 plus 100. That's this 100K and this 1K, multiplied by the Thevenin voltage of 2, and then we'll multiply by the gain of the amplifier, which is 10, which gives an output voltage of approximately 0.2 volts. Do remember that this Thevenin circuit is a stand-in representing a sensitive sensor. For example, maybe you used a chain where you had a sensor, an op-amp buffer, and then a microcontroller. If you used the wrong op-amp configuration, you've destroyed the integrity of that system. Once again, we'll be using the waveforms software, which is used to drive the Digilant analog discovery. This is the power supply section here, the waveform generator, and the oscilloscope. Currently, the oscilloscope is looking at the non-inverting op-amp. You can see that the waveform generator is providing a 100 millivolt signal. That is a peak voltage. You can see that in the oscilloscope here. Here's 100 millivolts, so that's 100 millivolts positive and 100 millivolts negative, when the oscilloscope is set for 50 millivolts per division. Now the output appears to be almost identical to the input, and the output is set to 50 millivolts per division, which implies that we have a gain very close to 10. Consequently, we can assume that our non-inverting op-amp is not loading down the signal generator. Let's go ahead and switch to the inverting amp and see what that looks like. Now that we've switched, you can see that it makes quite a difference. Our inverting amplifier, with its 10K ohm input impedance, has severely loaded the signal generator, which had a 100K ohm Thevenin impedance. To make things a bit easier, I'm going to increase the waveform generator output to 2 volts. Let's change channel 1's volts per division to match. Notice that channel 1 and channel 2 are now set to the same volts per division. So even with the amplifier installed, you can see that the amplitude of the output is less than the amplitude of the input. Shifting to the voltmeter, channel 1 has a 1.4 volt input, and channel 2 has a 1.3 volt RMS output. If we multiply this value by root 2, we arrive at the 1.8 volts that we calculated earlier. As we conclude, I hope you'll never forget that the input impedance is very different between the inverting and non-inverting op-amp. In many applications, you would be better off using the non-inverting input because it has a higher input impedance, which is to say it's less likely to load down your circuit, resulting in better performance. While the non-inverting op-amp input impedance is high, I should mention that it is not infinite, and perhaps that's something we can explore in a future video. Until then, I thank you. Please leave any comments, questions, or concerns in the space below.